going to tell us about two games and other stuff.
Hi everyone, thank you for letting me invite myself to this workshop. So it's a long story, this 2-to-2 game stuff. It's a sequence of like 4 papers where Arity and myself are on 2, and there is some contribution from Barak and Kotari and Steurer, and I thought I would also talk about some newer work with Noam Lifshitz and David Ellis, but when I prepared the talk, I realized that I will not have time for this. Right, so I need to define these 2-to-2 games, and it all starts with gap problems. This work started when PCPs were about approximation and gap problems and not about blockchains. So it's like regular old NP problems. You have a graph and you want to know what? A network, yeah. So maybe you want to find a maximal click, so a maximal fully connected set of vertices. So the gap version, maybe a 1/2 0.1 gap version of this, is where you're promised that in the completeness size, either there exists a click of size 1/2, covering half of the vertices, or the maximal click is much tinier, is only 0.1 of the vertices. And the gap version is given this promise to distinguish between the two. So that's a gap problem. And if you know that a gap problem is NP-hard, then you also know that the problem is hard to approximate. That's a simple exercise. And the way that usually you show that a gap problem is hard is via PCP, probabilistically checkable proofs. That's one way of looking at it, or and it involves, at least in a very significant way, some local to global phenomenon. So inside typical PCPs, you will find error-correcting codes and local tests for them. So an error-correcting code can be Reed-Muller, Reed-Solomon, Hadamard, long code. There are many codes. But for a PCP, you also need a query-efficient code test. So that's a code, that's a test that queries only Q entries from the entire word. That's the local part. And then it either accepts or rejects. And then if the probability of acceptance is greater than some parameter delta, then you know that the word that you're given is close in some sense to a code word. So that's the global part, right? Because the code word is global and you only checked a constant number or a very small number of entries. And it's not clear how to get a PCP from a code test, but it's clear that the code test that you use for the PCP either determines or at least limits the parameters of the PCP that you get. So you want code tests with good properties. And here's something that I should have said at the end, but maybe I will never get to it. So I will say it now, that there is some deep, although not totally understood, relation between efficient tests for codes and expansion or small set expansion. And there's also some relation between this and hyper-contractivity. And these relations play a big part in this work. Hopefully, we'll be able to see some of it. OK, so here's a quick, well-known example of a code test. So the code is the set of linear functions from f to the k to f, where f is some small field maybe. And then the Bloom-Rubinfeld test says, OK, you're given all the values of this function. You want to know that it's linear. Just pick 2 points at x and y and see if f of x plus f of y really equals f of x plus y. And if f is really linear, then you have completeness 1, yeah, right? You accept always. And it turns out that you can get the soundness to be half plus epsilon. Anything greater than 1/2. Of course, a random function will satisfy this equation with probability 1/2 if for a field of size 2. Right, and building on this test, Hastad gets optimal hardness for linear equations with 3 variables in each. And this is a 3-query test, right? You check at x and at y and at f and at x plus y. And for getting 2-to-2 game hardness, we will need only 2 queries. Right, so I will show you what unique games are. Well, unique games and 2-to-2 games are similar. I will show you both of them, and then it will be clear why we need 2 queries. So an instance of unique games is a system of linear equations. That's not the most general definition, but it's actually equivalent. So I'm not cheating here. With stress on here. So you have a bunch of linear equations. Each equation has just 2 variables over some field modulo q, where q is a large constant. And you want to solve as many of the equations as possible by assigning the variables. So just as a remark, max cut, which is a well-known optimization problem, is the case where q, the size of the field, is 2. Right, and the unique games conjecture of Koch says that distinguishing whether you can satisfy almost all equations or whether you cannot satisfy almost none of them, that's NP-hard. At least that's the conjecture, if you take q, the size of the field, to be large enough. This seems to be a strong conjecture, so we assume a lot, but it's also powerful because it gives a lot if you assume it. Right, so that's the conjecture again. And here are some of the things that you get from it. You get a tight, you know exactly what is the best approximation for many problems, like max cut, this max click that I mentioned before, matrix norms, two-sat, scheduling problems, many others. And actually, there's a theorem of Raghavendra which is very surprising and strong, which says that in some sense, if you assume the unique games conjecture, there is one particular approximation algorithm that gives the best possible efficient approximation for all constraint satisfaction problems. That's the theorem, but it somehow holds even in the cases that it's not stated for. So it's really a meta theorem. So if the unique games conjecture is true, then there is, then approximation algorithms are done. Of course, that's not completely true, but never mind. So so that makes the unique games conjecture interesting. We want to know if it's true. There are integrality gaps that point towards the truth, towards it being true. Koch and Moshkovitz have some candidate construction that if anyone manages to analyze, maybe it will give something towards the unique game, some weak version of it. There are also other groups that worked on algorithms that try to solve this gap problem. So there are algorithmic approaches that are non-trivial and give some strong results, although they do not solve unique games in polynomial time. And there's more to tell, but I will continue. So yeah, but we still don't know, and therefore we study similar things. So here's a 2-to-2 games conjecture. So you remember that in the unique games, we had a system of equations mod Q. That's a good time to say why it's called a unique game, right? When you have an equation, xi minus xj equals 7, this means that for every assignment for xj, there is a unique assignment for xi, which makes this equation true. So that's a one-to-one relation between assignment to one variable and to the other. For 2-to-2, we need a 2-to-2 relation, and therefore, instead of equations with one b, we have equations with two b's, and any solution that gives either this or the other is accepted. So that's 2-to-2 games, and here I am cheating a little, but never mind. And in the same paper where Subash stated the unique games conjecture, he also stated the 2-to-2 games conjecture, which is that it is NP hard to distinguish if you can satisfy all of these constraints or you cannot satisfy even delta. Yeah, and here you have perfect completeness, which you cannot have with regular linear equations, but that's a minor point for this talk. Yeah, so that's a weaker conjecture than the unique games conjecture, although it still has some interesting applications. And in some way, which I will make clear in the next slide, this is halfway to a unique games conjecture. That's a very formal way of defining the halfway, but never mind. Yeah, and the point is that if you take all of these papers plus this contribution by Barak, Kotari, and Stoller, you get almost the 2-to-2 games conjecture, except that, first of all, I switched the order between delta and 1 minus delta, and also instead of 1, I have 1 minus delta. So it's almost perfect completeness instead of perfect completeness. Right, yeah. By accident, yes. Yeah, no, it's not. Yeah, it's not part of the result. Right, yeah. Right. So yeah. So what do you get from this now theorem, the 2-to-2 games theorem? Well, you get optimal hardness of approximation for various problems. You get less than optimal, but still good hardness of approximation for problems like the clique, the gap clique that we discussed, and k-coloring and for-coloring. But one interesting thing is that you get that the unique games is hard for the gap version where you have half instead of 1 minus delta. So in that sense, it's half the way, because no constant was known before. Now we know 1/2. If we manage to multiply it by a factor of 2, we are done. Yes?
You say less than optimal. I mean, we don't know, right? This could be optimal or no? Like,
sorry, what is less than optimal?
You know, for the gap clique, for example.
It's less than optimal in the sense that if you assume the unique games, you get something stronger. Right. Yeah. Less than the theoretical optimal. Yeah, yeah, it might be.
And what was the previous thing for gap clique that was known?
Yeah, so that's some constant versus delta, and the optimal is 1/2 versus delta. The theoretical optimal. So theoretically, even if you're staring at a graph where half of it is a clique, you cannot even find delta clique. Right, and the fact that the 2-to-2 games implies this actually kills a lot of the algorithmic approaches to unique games, because these approaches do not distinguish between completeness half and completeness one. So at least it's a strong indication that the attacks on the unique games conjecture, the current attacks, will not work.
Unless they can also solve set.
Unless P equals NP, yes, right, yeah, that's always an option. Okay. So yeah, so you want to get hardness for 2-to-2 games, and as I said, inside you need some code that fits what you want to get. Yeah, let me talk about agreement test for codes, which is the type of code test that we'll use. So you want to encode a set of code words, some nice functions over some domain that have nice properties. And these functions you want to somehow encode in a way that you can test. Maybe low-degree functions, for example. So here is the domain. So you want to encode a function that is defined over all the points here. The entries of the code will not be points. They will be collection of subsets of the whole domain. And an encoding of a nice function will assign each of these subsets with the restriction of the function to the subset. So if, for example, this is the set of functions of degree 5, we will only allow restrictions that are 5-degree polynomials on these subsets. And then the test will choose by some distribution 2 different subdomains that have some intersection and do the obvious thing, which is to test that the assignment that we have on one subset and the assignment that we have on the other agree on the intersection. So that's an agreement test. Yeah, and for completeness, of course, if these are all restrictions of some global function, we will always accept. So we have completeness 1. And the sum parameter is delta if we can somehow prove that when the test accepts with probability delta, then there must be some global function that agrees with many of the subdomains. And many can have many meanings, and you really need to be careful about what it means. Right, so here's one good thing about an agreement test, at least the way I described it. It has 2 queries, which is good because eventually we want to get equations with 2 variables in each. So that's the same 2. It's not the same 2 as the 2-to-2. The 2-to-2 means that for any assignment on this subdomain, there should be only 2 assignments on this subdomain that can agree with it. Okay, let's do it slow. Okay. I'll return to that. Let me just say something about agreement tests. They have a long history. I will not describe all of it. I will just mention a few. So there's Rubenfeld Sudan, which they tested that the polynomial is of low degree by having subdomains that are lines and points and checking agreement between them. There's Goldreich and Safra that use similar tests for tensor products of codes, but they could not give a low parameter soundness, and we want soundness delta, which is small. There is Raz and Safra. They used only subdomains that are subspaces with a small dimension, maybe planes, and they got low soundness. Yeah, so the point there is that when the domains are planes and they intersect on a line, a low-degree polynomial on a line is still a code, and then you can just test on a single point. Okay, I will not go into that. And there's Aurora Sudan, which did the same, but with lines and points. Right, okay, and here I go back to where I was before. I want the Arity to be 2. I want an agreement test where if I know the assignment of one variable, it determines almost completely the assignment of the other variable up to maybe there could be 2 options. So let's see how we can make the Arity of an agreement test be 2. Right, so yeah, so the definition of the Arity is what I said. You fix an assignment for one variable, and you only need, and there could be only R options for the other variable. So in Raz Safra, when they tested 2 planes, if you wanted low soundness, but then you had the Arity larger, so we need Arity 2, and for, yeah, and that's, in some sense, if you want the unique games conjecture, not the 2-to-2 conjecture, you need Arity 1 in some sense, which is not clear, so that's why we don't know how to attack it.
In low soundness, you mean any constant?
Low soundness, yeah, means any constant greater than 0. That's what we want. Right, so but if we start from Raz and Safra, so we have these planes, and we pick 2 planes that intersect. If I know the assignment of this plane, there are still many options to an assignment for this plane as long as the field is large. So we need a small field. Optimally, we need a field of size 2. And also, even random assignments, especially when the field is of size 2, will agree with some constant probability if I only look at planes. So actually, instead of planes, I need subspaces of larger dimension. So still constant, but a constant that depends on the soundness that I want to reach.
But it sounds like this approach, you'll also be able to get sub-constants.
Right, it depends on the parameters, so yeah. Right, now, yeah, and so now you have some subspaces that intersect. You want the value on one to determine almost completely the value on another. So you want a minimal freedom for the assignment of the other. And for that, you need the codimension. Like, you want the other to be of dimension maybe 1 more of the intersection. Because then, assigning the other one only requires choosing a value on 1 new base vector. And you also want a linear degree. So let's try to sum this. Now you have the global function will be linear. And therefore, on each domain, you expect a linear function. Right, and then when you assign one domain, it almost fixes the assignment to the other domain, except for 1 new base vector that you need to add, that on that, the function can be either 0 or 1. So there are only 2 options. And when you realize that, you get what is called the Grassmann test. So that's the Grassmann cotest, which appears in the first paper. Yeah, so you have the field is of size 2. You are going to encode functions from f to the k to f, where k is a very large constant. And the subdomains will be subspaces of dimension L, which is a small constant, small large constant. Right, and yeah, and to encode, you assign, to encode a function f to each entry L, you assign the restriction of f to L. And the test is you pick two subspaces that intersect in the largest dimension possible, and you accept if they agree on the intersection. So that's the agreement test that we need to get 2 to 2. Here's a picture. And as I already said, this is a 2 to 2 agreement test. Once you fix the assignment to 1, there are only 2 assignments to the other that agree with it. Yeah.
Do we know what happens, or does it even make sense to consider this type of agreement test for, say, quadratic or cubic functions?
It makes sense, yes. But the point is that if these were quadratic functions, even if the field is of dimension 2 and the intersection is the largest possible, you lose the arity.
But just as an agreement test.
As an agreement test, yeah, it makes sense to consider it.
And the analysis of this test, does it tell us anything about the analysis for that test as well? Or
Sorry, analysis?
understanding this test for linear functions, does it already tell us something interesting about?
Not immediately, not that I see. Even analyzing this test is quite non-trivial, and I don't know how to generalize immediately.
That has scope of getting perfect completeness. No?
Yes, right. Yeah, that has hope of getting perfect completeness. Yeah. So no, I'm not saying it's not interesting. I'm just saying I don't know how to do it. Yeah. Right. Obviously, yeah. When everything is linear, you can't get perfect completeness. So yeah. Right. So now the question is, it obviously has perfect completeness. It's only the soundness that remains. So if we can get delta soundness for any constant, positive constant delta, then we are done. So let's assume that this test has soundness delta, and let me in one slide say how do you get the 2 to 2 hardness result for the gap 2 to 2 hardness. Even that is complicated. And eventually, you don't get delta soundness, not in the usual sense. So eventually it's even more complicated than that. But let me just say, assume that you do have this delta soundness. What would you do? So, okay, if you're an expert, you'll know this, and if not, you'll get hopefully something from this slide, but maybe not a lot. So you start with a PCP theorem. Sorry. And you get by a trick. So the PCP theorem is itself hardness for some gap constraint satisfaction problem, and from that you get some even smaller gap hardness for label cover, and then you do parallel repetition, and then you get a big gap for label cover, and then the standard thing would be to use the variables in the label cover and encode them via whatever new shiny test that you have. In this case, it's this Grassmann code. It doesn't work because we only know how to encode linear functions. So we can only encode linear functions. So instead, you can follow Hastad's tracks and encode everything by the long code, and get hardness for 3 linear equations, mod 2, and then from that get a small gap for label cover, which is linear, and then, and by using hardness for 3 lin, you lose completeness, and then that's a small gap. You want a large gap, so you apply parallel repetition, and then you get a linear label cover with a large gap, and you apply Hadamard encoding and to the variables, and Hadamard encoding is an encoding by linear functions. So to that, you can apply the Grassmann encoding. And then by, you need this decoupled version of this Grassmann test, and you need folding and other things. But eventually, you get the hardness that you wish. This is all assuming that the test has soundness delta. Okay, so now forget about that. Let's return to the Grassmann test and think whether it really has soundness delta. So now soundness. Okay, so forget all this PCP stuff. You have someone gives you a linear function on every subspace of constant dimension. And if you pick two that intersect with on a codimension 1 subspace, then there's a probability of at least delta that they agree on the intersection. Does it imply that there is a global linear function that agrees with a non-negligible fraction of the local assignments? So that's the question. That's the soundness question. And the answer is no, there doesn't need to be such a global function. So let me give you an example. But before I give you so I'm going to give you an example of an assignment that satisfies the test, but there's no big global function. But before that, let's do this trick. Suppose I pick L and L prime randomly, except with the constraint that they intersect on a codimension 1 subspace, and let X be some point in L. What is the probability that X is also in L prime? Okay, so this is 0. This is the subspace L, and hopefully the next, so, and here is X. What I know about L prime is that it contains a subspace of codimension 1 inside L. And this is a field of size 2. So a subspace of codimension 1 contains half of the points. And therefore, the probability that this, so here is a partition of the space to the two cosets, and the probability that X is contained in the one that also contains 0 is 1/2. And that's the other subspace that contains this coset that contains 0. So the answer is roughly 1/2. There is a minor correction that you need because of 0, but so about 1/2. Which, here's another way of saying it. Define Zx to be all the subspaces that contain X. That's called the zoom-in set for X. So that's all the L's that contain X. And what we just said is that Zx has a staying probability of 1/2. If you start at an element of Zx and then you go to a neighbor, this neighbor is also going to be in Zx with probability 1/2. Another way of saying it is if you consider the pairs of subspaces that the test considers, you consider them as a graph. So you have an edge between two subspaces that the test can check both. This graph has sets such as Zx that are completely not expanding. Right? If you do a random walk inside Zx, at each step there is a high probability of staying inside Zx.
You're connecting everybody of codimension 1, you're saying? Or?
Yeah, so you're connecting two subspaces if their intersection is of codimension 1. And in this graph, Zx is a non-expanding set. So this is not so we took the test, we used it to define a graph, and I just told you that this graph is not expanding, and that's actually the reason why I can construct an assignment that satisfies delta fraction of the tests, but is not global. And the way to do it is just, here's the zoom inset again. And now, for every x in the original big domain, just pick an arbitrary global, randomly, a global function, a global linear function f of x. And then, for every subset L that contains x, just assign it the restriction of fx. So actually, you need to sort all the x's in some arbitrary fashion, and then the first x that is also contained in L, it gives the assignment to L. And because Zx has this high staying probability, when the test considers L and its neighbor, there is a high probability that they are both assigned by the same x. And therefore, the test will accept with large constant probability. But each of these sets, Zx, is actually tiny. Right? What is the probability that a subspace of some small dimension will contain a specific point x? It's really tiny. So you have a huge number of these sets and no global function, because for each set, there's a completely different assignment. And there's, of course, more. How much time do I have? How much more is there?
About 15 minutes or something.
Okay. Right, so this zoom-in set, looking at all subsets that contain a certain point x, that's a non-expanding set. There are other non-expanding sets that you can use to give other counterexamples. So there's a zoom-out set where you look at all subspaces L that are contained in some large subspace W, and you can do the same tricks there. Also, the staying probability is 1/2, and you can get a counterexample from that as well. Right, so there is no delta soundness in the usual sense. Delta soundness in the usual sense, right? Because we've seen two counterexamples. And when you encounter such counterexamples and you really want to get something, then usually what you say is, maybe these are the only examples that exist. And usually it's wrong. But in this case, it is. It is right. It is correct. It works. So this was a conjecture at some point that if the test accepts with probability greater than delta, then you can then there is a global function that maybe doesn't agree with with a large fraction of all the subspaces, but it does agree with a large fraction of subspaces that are contained in some small codimension subspace W and contain a subspace of small dimension Q. So there is some combination of zoom in and zoom out, where inside that tiny set of subspaces, there is a global function that agrees with a non-negligible fraction. Right, so just like X was used to assign all the subspaces in ZX, so for the subspaces in ZX, there was a global function. It was just that ZX is a tiny set. So that was the conjecture, and it was eventually proven. Yeah, that I will not go into this remark now. You all seem too tired for that.
What is it? Is exactly ZQ to the...
So ZQ is all the subspaces that contain Q. ZW is all the subspaces that are contained in W. And this is all the sets that contain Q and are contained in W. So this is a zoom in out lens something. And when the test accepts, there is such tiny tiny part within the whole entries of the code word that do agree with some global function. And from this you can get the 2-2-2. If you believe that, then you can get the 2-2-2 conjecture. It's not easy because that's only you get a global function that agrees with a tiny fraction of your code word. So you need to do some extra stuff, but that works.
Maybe uniqueness of Q and W.
I don't need uniqueness of Q and W, and actually what I do use is that if there are such Q and Ws, because that's such a tiny set, then they can't explain all of the acceptance probability of this test. There must be also either other Qs and Ws that also exist. So I can take this Q and W that work, ruin the assignment to the subspaces here. The acceptance probability of the test will still be rather high because I only ruined the tiny set, and therefore there must be other Q and W that work. So there are many of those. There's no uniqueness. And actually that's what we need. So if there, so it's a little misleading. If there exists Q and W, there actually exist many pairs of Q and Ws. Right, but you have a two-prover system, and they need to somehow agree on which Q and W to look at. There's stuff to do. There's a lot of stuff to do. Right, and then, okay, I will say only a few words on what goes on. So basically here, the conjecture just says that the code test works, maybe in a weak way, but it works. And if we have the code test, then we have to work, but then we get the 2-2-2 conjecture. Now we need to show that the test works. And the first thing that we did is to think, okay, maybe the test doesn't work. And if it doesn't work, there must be other small sets that have high staying probability, other than the kinds that we already know. Right, so this is the graph that I already defined. And there was another conjecture that says that the only sets that have a high staying probability are sets which are of this form, or at least have some large set which is roughly of this form. And from here the story, I will not go with the slides because there's not enough time. I'll just tell more or less the story. Right, so we, at least this version, we managed to prove not for all delta, but for some parameters in this paper. And there was a paper of Dor and Muli and Subash that got the whole delta. So at least we knew that this works in terms of the structure of the graph. It has the small set expansion properties that we thought it should have. But Barak and Kotari and Steurer noted that there's a maybe 3-line proof that shows that if you have this expansion, this structured expansion property of the graph, then you also have that the test actually works in the sense that is written here. And therefore, we have the 2-2-2 conjecture. And the way that you prove that the graph has the required expansion properties is by looking at, now I forgot the word, spectral decomposition of the graph. And yeah, but these are not magic words. Spectral decomposition is just the first step. And then there's a lot of very complicated work. And this work that I was grayed out with Noam and David, we managed to reprove this property in a way that is somewhat simpler. But unfortunately, I will not have time to say anything more about that. Right, so yeah, so here are other slides. And here are some open problems. So yeah, it would be nice to prove the unique games conjecture. So I have to put it there. Right, but this work required something that I'm not sure I saw before, certainly not in computer science. There's a lot of work about expansion and even the relation between expansion and codes. The original linearity test of Bloom, Luby, and Rubinfeld, I'm not sure that this was the original proof, but one early proof for the soundness of this test uses expansion in some graph. So this structure was known. The new thing here is that we don't have a graph that is expanding. We have a graph where we know the structures of the sets that are not expanding. So we don't have expansion. We just know that whenever expansion doesn't work, there's a specific reason for that. And we somehow manage to still use it, but it might be usable in many other situations. There's no, that's not low degree. That's small set. Small set and low degree somehow consume the same space in my head. And yeah, and of course, you use it for interactive PCP or blockchains or whatever. So that's also an option. Yeah, and I recently took drawing as a hobby, so that's also true.
So maybe I missed this, but from the half comma delta hardness for UGC to go all the way down to something closer to 1, is there, so this approach would not work, but if there are other, what parameters of this test translate immediately to the UGC hardness?
Okay, I'm not sure I understand the question. I'll answer it anyway. Because, okay, there's a, that's just one remark that I should have said during the talk, which is if you have an instance of 2-to-2 games, and you know that it's hard, so either it is completely or almost completely satisfiable, or there's no assignment that satisfies even delta fraction of the constraints, it's easy to make it into an instance of unique games that is on either side of the 1/2 and delta gap by just for each constraint is this 2-to-2, like for each assignment here, you get 2 options on the other side. So just select one of them randomly. So this changes the constraints from 2-to-2 constraints into 1-to-1 constraints. And the same assignment that satisfied all the constraints before, now it will, in expectation, satisfy 1/2. And it also works on the other side of the gap. So, so the way that you get to 1/2 delta unique games is by a simple exercise. And this 1/2 comes from the inverse of 2 in 2 to 2. And therefore, as I said, if you want to go from 1/2 to 1, you need, at least using this approach, you need agreement tests where when you see, the test looks at 2 variables, but when it sees the assignment to 1 variable, it already knows exactly what the assignment of the other variable should be. And that seems to create a lot of problems. So we do know tests that are like that, which is, I hinted towards that in the talk. We do know tests that are 1-to-1, but test is not enough. What we need is to be able to use the test not just to check that something is a code word, but we need a decoupled version where we have 2 code words, and we need at the same time to check that one is a code word, the other is also a code word, and that the things that they encode satisfy a certain constraint. And that we don't have, and this 2 in the 2-to-2 enables us to do it. And it's, at least to me, it's not clear at all how to move from this to something that approaches the unigames.
You're saying somehow in the 2-to-2, it's enough that you just individually check that 2 things are code words?
No. There's much that goes into it. It's not simple, but it's doable. Yeah, I'm not sure. Okay, I cannot really tell you how it works, but just as a vague intuition, if you have 2 linear functions, one on f to the k, and the other also on f to the k, but it's a slightly different k. So you have like a Hadamard encoding of a set of variables, and a Hadamard encoding of a slightly different set of variables. In these 2 Hadamard encodings, there are many subspaces of small dimension that are shared between those 2 encodings. And you can somehow check the consistency of one. So you can check the consistency of a subspace in one Hadamard encoding and versus a subspace that actually comes from the Hadamard encoding of a different set of variables, as long as these sets are almost the same.
And for the unique games, you would need that they're exactly the same.
Yeah, and for the unique games, you need that they are exactly the same, and then it means that instead of doing a small step, you're doing a 0 step. And yeah, and there's a big difference.
Questions?
Thanks, Scott.